Let's look at a few things that will help us with our calculations. First of all, you need to be able to convert between millimeters of mercury for gas pressure and atmospheres. Our equations require that you use atmospheres. So to convert, you just take your millimeters of mercury and divide by 760. The 760, we treat it as exact so it does not affect your significant figures. If you have 4 significant figures in your millimeters of mercury pressure, then you will have 4 in your atmospheres of pressure. You've probably seen this one before. To go from Celsius temperature to a Kelvin temperature, you're going to add 273. This 273 can affect significant figures. It's not exact. So as long as the temperature that you're using here doesn't go beyond the ones place, this is good enough. For my lecture, my quizzes, my exams, 273 is fine. But for this experiment, we're going to use 273.15, a few more digits there. So just on this experiment. Another thing I need to show you is this other equation. This equation is one that you deal with in the lecture part of the class a little bit more. There is one post-lab question that uses this equation, and what's different on this one is N. The P, V, and T and R are all the same as on the equation we're using for molar mass, but N is number of moles. In other words, number of gas particles. So don't get that confused with molar mass. A lot of times that's what happens. So for example, it's easier than it looks. If your problem says something like this, if that's part of your problem, then what is N? N is 1 mole. And since 1 is written out, this is an exact number. Okay. So what's interesting about this equation, the ideal gas law, is that the molar mass of the gas is not in there. So this equation really doesn't care, or it doesn't matter what type of gas it is, as long as we say that it is an ideal gas, which means a gas that it behaves this at basically at low pressures and high temperatures. Gases will behave such that this equation predicts the behavior. So we call those ideal gases under those conditions. And under those conditions, it doesn't matter what the gas is. It doesn't matter how big the molecules are themselves. Anyway, you'll be working one of those. Now this next example is an example of the problem that you work for the experiment to determine the molar mass. So this is all of the givens, and you'll need to be able to do this calculation for your quizzes and your lab exam and so forth. So let's look at what we should do. So we have a mass, we have our M, we have a volume, we have a millimeters of mercury as a pressure, and we have a temperature. So we have MT, PV, we know R, so we can plug those in. Before you plug them in though, check all of the units and make sure they're in the correct units, because we know that R has liter atmospheres per mole K. So I need to match to that. Otherwise the units won't cancel the way they need to. So let's just start with, well, it looks like mass is already in grams. Actually, that's not even in there. The grams from mass will end up being divided by the moles in R to give you grams per mole. So mass is good. The volume, though, needs to be in liters instead of milliliters because R has liters. So let's change that right here. This is a simple conversion. So there's our V. We will use that V. What else do we have? We need to fix our pressure. It was given to us in millimeters of mercury. We need to divide by 760 to get our pressure in atmospheres. And again, this number had 4 sig figs. We treat this one as though it's exact, so our pressure has 4 sig figs. Looks like we need to convert our temperature as well. Our temperature is 100 degrees Celsius. And by the way, this is what I want you to do in your experiment in the lab. In fact, if you want to just fill out that on your report sheet, the temperature in Celsius is 100.0. And with that many sig figs, 273.15 is what we're going to add to that. Remember, I wanted to use extra digits. So there's our temperature in Kelvin. Let's look at what happens with the sig figs though. This is going to get cut off right there. So we're going to say 373.2 Kelvin. That's our temperature. And that is the exact temperature you'll use in your experiment. Okay, so we have everything in the correct units. We're going to plug into our main equation. Our main equation was this one. So just plug in all of our numbers. We plugged in all of our numbers, and if you want to, you can look and see that all the units are canceling. See what I'm talking about? This K cancels with this one under there. That atmosphere cancels with this one here. This liter cancels with this one down here. And then we're left with 2 units, grams over moles, which is what we would expect. Now put all of this into your calculator and make sure you get what I'm getting, because there's a common mistake when you enter these into your calculator. My calculator gives me this number. If you're getting a number a lot different than that, make sure that you're dividing by both things on the bottom. In other words, you should enter this in your calculator, 0.572 times 0.0821 times 373.2 divided by 0.9832 and then divided by 0.3120. Always hit the divide button before both things on the bottom. So check and make sure you're getting that. It's a common issue. And then we need to round this to the correct number of sig figs. It looks like I just need 3 sig figs. And we need to know the units. What are the units? It's molar mass, grams per mole. Okay, so that's our answer. And we should ask ourselves, does that seem like a reasonable molar mass? It does to me. I mean, if you've calculated some molar masses, you know that, usually they're in the tens to hundreds, something like that. That seems like a reasonable number. What if I had gotten a number, just for example, what if it had said something like Would that be possible? That's not possible. Molar masses can't be that small. Why? What's the smallest molar mass that you could get? The smallest molar mass is 1. For hydrogen. Hydrogen is 1 mole, 1 gram per mole. Okay, so that's not possible. Let me ask you this. What about if I had gotten something like this? Is that possible? Well, certainly it is possible to have a molar mass that large, but something with a molar mass that large would not be a liquid at room temperature and would not vaporize at 100 degrees C. Remember about attractive forces is that they add up. So if you had something that big, the molecules would be so attracted that would probably be a solid. Okay, so in our experiment that will not happen. Just so you know kind of what to expect, your molar masses will come out for this experiment. Your molar masses will come out between 50 and 150 grams per mole. I tell you that because some of the simple mistakes cause it to be way, way off, and I would rather you go back and figure out what's going on rather than being counted off for your accuracy when you have some huge or some tiny number.